This lecture video is going to cover correlation. Correlation measures the relationship between two numeric variables. And these are variables that are dealing with paired data as opposed to independent data. For instance, if we were to look at the number of hits a Major League Baseball team has in a season and the number of wins, that would be paired data. If we were to draw this out, we have an x-axis and a y-axis. X will be using hits, and a y will be using wins. And if I was to label some axes in a season, typically teams have around anywhere from 1,000 hits to 1,500 hits. So I'll make these our axes every 1,000. Wins typically range between 50 to 100. The San Francisco Giants in 2019, a Major League Baseball team, they received hits of 1,332 and wins 77. So what we would do is we would go to that on our graph. We have 1,300 roughly hits and 77 wins. And then we would place a point right here. And we could do this for all of the observations in our data set. Maybe baseball teams. Hits and wins. We could do that with height and weight of a person. Amount of rainfall and crop production. And so we're dealing with paired data, and we can use a scatter plot, something called a scatter plot, to visually display paired data for two quantitative variables. What we now want to do is measure the relationship between these two variables using some type of quantitative metric. For us, we're going to be looking at something called the correlation coefficient. And what this correlation coefficient does is it measures the linear relationship between two variables. We denote that as R, and this is for a sample of data. So R denotes the sample correlation coefficient. The Greek letter rho represents the population correlation coefficient. And what this correlation coefficient does is it standardizes the linear relationship between your two variables by the bounds -1 to +1. There are three extremes for correlation coefficient. One represents a perfect positive linear relationship. -1 represents a perfect negative linear relationship. And 0 represents no linear relationship. So these are kind of our three extreme scenarios, and then we can have correlation coefficients between those values. Let's go look at some. For graph A, we have a correlation coefficient of -1, and that's because your points are following a perfect downward line. Graph D, +1, because they're following an upward line. It's not even about the slope. You could have points that are not as steep, but as long as they're perfectly following a line and they're going upward, both of these correlation coefficients would be 1. So the slope is not taken into account. We can see as your line gets less and less perfect, your points are going to slowly get closer to 0. If we look at graph C, is the line going upward? Is the line going downward? Is the line going horizontal? What is this line? We can't really draw a line through that data. And therefore, our correlation coefficient is close to 0. For the last graph, graph F, there definitely seems to be a relationship between X and Y. However, it's not linear. And notice your correlation coefficient is not picking that up. So even though there is a relationship between X and Y, it's not linear. Therefore, your correlation coefficient does not pick it up. Now, one thing we haven't done is talked about how to calculate these correlation coefficients. And to be honest, that's not the most intuitive formula. So for us, we're not really going to worry about calculating the correlation coefficient for us. I just want us to understand, if we were to look at a correlation coefficient, what does that tell us? What can we learn from it? So let's see what I mean. Here we have a set of actual data, and these are our 11 observations, weight and height for young adults. So the X represents weight, Y represents height. If we were to make a scatter plot of these observations, it would look something like this. What we want to imagine is a line going through your data, a straight line going through your data, and how close your points are to the line. It seems like here your points are generally following an upward trend. They're not perfectly following it, but they're generally following it. The points are relatively close to the line. If you were to calculate the correlation coefficient out, you would end up with 0.82. Well, okay, what are we supposed to do with that number? Right? Yeah, we're quantifying this linear relationship, but now what? We can use this number to give us a general guideline of that linear relationship. And so for us, there's going to be 4 categories of strength. To talk about the strength of a linear relationship, if we're between 1 and 0.7, we'll call that a strong linear relationship. 0.7 to 0.5, moderately strong. 0.5 to 0.3, moderately weak. And 0.3 to 0, we'll call that weak. So we have 4 different types of strengths. And then we just have 2 different directions. Is the line going upwards or is it going downwards? So here's a general guideline about how we can talk about these correlation coefficients. Right? After we get them, what have we learned? Right? And we can use these general rules of thumb to bring context to them. So what this graph would be saying is that there is a strong positive linear relationship. And that point's very important. Strong positive linear relationship between weight and height. And so this is how we can kind of talk about that relationship once we get that correlation coefficient. So you may have heard this before, but what we want to think about is if 2 variables have a strong correlation or a strong correlation coefficient, does that mean that one causes the other? Well, the big answer to that question is no. Just because 2 variables are strongly correlated or not strongly correlated does not mean one causes the other. This could be due to something which we call confounding variables or a confounding variable. If we think about our example with Major League Baseball teams, trying to look at hits and wins, we have a bunch of different data points here. There is somewhat of a linear relationship between hits and wins. However, if you know baseball, inside of the variable hits are different types of hits. There's a single or singles, doubles, which you go 2 bases, triples, which are 3 bases, and home runs, which you score a run, at least a run. A much better indicator of how many wins a team will have is based on home runs and doubles if you actually do some studies. These are much better indicators of how many wins a team will have. So inside the variable hits are the variables doubles and home runs. This is why we shouldn't say one variable, quote, causes the other. There could be confounding variables which have an effect on both X and Y that are, quote unquote, the reason for the correlation, the cause for the correlation. So the question that we need to think about then is, why is correlation useful? Right? Just because 2 variables are correlated with one another doesn't mean one causes the other. So what's the point of all this? Well, here's why this is important. Just because two variables are correlated, we can use that fact to make predictions. We can use one variable to make a prediction of another, even though one doesn't quote unquote cause the other. This is a very important concept. Using the fact that variables are correlated will give us insight into making predictions. This technique that we're going to be using is what's called linear regression. Linear regression will create a model or a function that's going to help us predict a variable using another variable or multiple variables. But typically what we'll be interested in is if our correlation coefficient uncovers a linear relationship. Well, then we can use that fact to make predictions. And typically, the stronger the linear relationship we have, the better predictions we're going to get.